in there. So put together this rather quickly about, sort of what are some of the things that led to this point in time with AI and everything that's going on with machine learning. Which direction is it sort of pointing us, and a little bit about what it might, a little bit around, directionally what it does for us as software people. So one note, I had created a slalom deck around something similar, a little bit more business focused. So I definitely stole a lot of those slides and put them in here. You'll notice them because they're a lot fancier than this slide, just for what it's worth. All right, so this is where it gets complicated because I have to keep switching. So a little bit of terminology, I guess. There's plenty of descriptions about the difference between AI and ML. Everybody has different, sort of degrees of opinions about it. There's certainly a lot more little pieces you could put inside of these bubbles about different subfields. But overall, AI itself is the broader term, and ML is sort of a subset of it. And the way you kind of try to think about it is the way it's laid out here is AI is trying to get a machine, to do anything that a human currently does and be able to automate it. And then the machine learning piece is obviously just that. How do you teach a machine to learn? Being able to learn is probably the biggest part of intelligence. So one is sort of required for the other in some way. So before I get too far, I want to do a little bit of history. So Wikipedia has some, a lot of this written up. I was surprised to find that, as well as other pieces and books I've read. It's kind of interesting to hear how things came about. I didn't go too far back. I think some of AI can go back into the 1700s, or what was originally considered to be some kind of automation. But for the place where I sort of, picked up was where they, the I think it was 1950 exactly, when Turing created his paper around machine intelligence and whether or not you could actually teach a machine to be intelligent. He came up with obviously the Turing test, which most people have probably heard of, which is how do you get a machine to be able to fool a human, and if you can, isn't that machine effectively thinking? And this kind of set the stage for the idea that it's at least a plausible idea that you could create a thinking machine. Shortly after that, there was this conference, Dartmouth, with a couple sort of logic, people who study logic. Also, there was Claude Shannon, this sort of modern father of entropy, and another partner he had from IBM. And the proposal of the conference was just kind of to figure out, and they thought that every aspect of learning could be sort of automated in some way, and that's when they officially coined the term artificial intelligence. After that, there was when the 1958 Frank Rosenblatt, I think that's the right name. He was actually, I think, a psychologist. He invented the first neural network, which is a very simplistic thing called the perceptron. And then you kind of dart off into these phases. The thing about AI and ML is it has this weird sort of colored past. It sort of stopped and started in a lot of different places, and people who have tracked it for a while had sort of broken it up, and this is the way Wikipedia kind of breaks it up into different phases. And 1956 to 74 is what they're calling the golden years. This is when a lot of research was being done about the fact that you could create an intelligent machine, and they predicted, a lot of researchers predicted within 20 years there was going to be a completely intelligent machine, but that would have effectively made it sometime in the 90s. There was the first chatbot invented that used NLP, this thing called ELIZA, and it was sort of this online. I think it was like a bit of almost like a therapist in some way. And there's a little screenshot of it up there.
That was around 74.
Was it? Okay.
Was it?
Oh, I don't know. I don't know the exact date, but yeah, it was during that period. I think it was definitely in the 70s, though. Yeah. And then there was also the MIT Advanced Research Lab that eventually became DARPA. And this is where the real funding for AI-like research was put together. And their whole idea was they were going to fund people. They looked for people with the right kind of mindset. They weren't necessarily interested in funding projects. And this was sort of the birth of modern ideas around a hacker culture. So a lot of really cool stuff going on at this point in time, a lot of research around what they thought might be possible. And then came what they called the first AI winter, which was sort of this dead zone of stuff where all of the research kind of dried up. And the primary reason was there was a lot of research being done around the feasibility and the complexity of certain algorithms, and how if there was not enough compute power, it didn't really matter how good of a, how didn't really matter if you could build a thinking machine if there wasn't enough reasonable amount of compute power to do these calculations and get things done in a certain amount of time. And so the funding in a lot of scenarios kind of dried up because everybody recognized that there was nothing on the horizon by way of hardware, et cetera, to keep this thing going. And then they entered what they call the boom, which is when there was first sort of expert systems design based on rule sets. That was the first time OCR was officially created. This first computer, this was the first machine that beat a grandmaster chess player. It was called Deep Thought. That was the precursor to IBM's Deep Blue. And then that's when the money came back as well. So after that, you get on to this next, what they call the second AI winter. Again, money sort of dried up, somewhat related to hardware again, but also there was a lot of research going on with this concept called Nouvelle AI. I'm not sure what Nouvelle means. I don't know if it was a person. People wanted robots. There was a theory out there that intelligence was actually born out of physical systems, and that intelligence itself had its roots in physics, or not physics, but the ability of something to interact with the world. So if you were going to plan to create an intelligent machine, it was going to be very hard to do unless that machine was actually interacting with the world around it. And that combined again with this sort of problematic issue of not having enough compute power, research dried up, and people started looking at robots like, the whole idea, but then that set everything back because now you got to design not just a thinking machine, but you've got to design something that can actually interact with the world. And then this phase, I don't know what they call it, but it was very close to recent time. This is when Deep Blue was created and actually beat Garry Kasparov. That was a huge deal. Tim, what year was that?
2011.
No. And then you probably famously saw when Watson beat some of the best Jeopardy people. I don't know if that was the actual final score there, but they had a Stanford robot that won the DARPA Grand Challenge by driving autonomously for 131 miles. And people started to recognize, because of this is during the time when Moore's Law was created, I believe. People had some recognition that over time, you would eventually get over the compute hurdle, or at least people believed you would. And so that renewed a lot of interest, and certainly recently. And then 2011 till now, you really have the phases of big data and deep learning. Big data, I think most of us here in the room know what big data is. I won't say it's gone, but it's probably past its heyday as a thing on its own, and now it's just more or less being seen as something to inform AI and ML and make it work. So, what are some of the things that you need to kind of kickstart the idea of being able to do AI and ML? So it's data. It's definitely a required ingredient. Lots and lots of data. Big data, again, big data formally is data that's considered sort of messy, sometimes unstructured. It's kind of coming from all different points, usually in the world. You don't necessarily have control over it. Within your organization, if you have a company, you might have some control over it. But it's considered data that is just sort of, very nebulous and out there. And it's up to you to kind of go and get it, corral it, structure it, and make it into something that you find useful. And then, the Web 2.0 scene, when the web became the read-write web, when people started to put content out there versus just strictly consuming. Social media added a lot of data, Twitter, Facebook, all the other pieces. Google itself certainly put a lot of data out into the web. as well as collected it. And then all of the other things we're seeing now from, sensors, voice. We'll get into a little bit around things like paper and what that means, but that's considered dark data or unstructured or semi-structured data. And then obviously the fact that everybody could just collect all they wanted, throw it into the cloud. And I found this thing here. It says that, I left it off there, that 2.5 quintillion, that's the number of bytes of data the internet produces in one day. I don't know how they came to that number, but it's a research company that it's apparently accepted as close to true.
Produces
new data. I assume it's new data. It's just 2.5 quintillion bytes of data per day produced by the internet. That's not that much. So all companies are looking, they all want data. It's considered the new oil. And by that, you mean it's kind of what's fueling the next move here, at least in technology. Collecting lots and lots of data is great. Companies are quickly realizing now that if you can collect really clean data or data that's been tagged, that's even better, because that's an expensive process to go and have to do that after the fact. And then all data really has some level of value. It's so cheap to store it now. A lot of companies just say, well, keep it, why wouldn't we have it? Obviously the issue is making sure it's secured and all those kinds of things. But I did this graphic here for the other presentation that I had. And this is kind of, I don't know if this is actually the formal breakup of the way most enterprises see their data, but that's the way, that's where a lot of companies are spending their time these days, is that there's sort of this recognition that, there's a small portion of our data, somebody says 20% here, that's stuff we can see, we know about, we know it's there. And then there's all this dark data, the under part of the iceberg that is there. And if we can get it out, it's useful. And this consists of things like, I've got invoices, I've got purchase orders in paper that I could scan in an OCR. I've got phone records, I've got emails, texts, all these kinds of things that, you could find useful in some way if you can get them out. And then as far as the kinds of pieces of AI and ML that are in use today and the data they operate on, this is really just showing at the lowest level of AI that's out there today is just basic process automation. I think, some of the stuff we do today in building software is in some ways considered process automation, workflow automation. There's actually companies out there now making a business out of sort of almost like running macros on desktops and automating things from different pieces of software and getting that done faster. And what this basically says is that, in order to do that kind of stuff, you need, pretty structured data. You can't go out and use process automation to go and grab, to scan in documents and figure out what they are. As you move up the chain, though, you're going to need less structured ways of learning about that data, and those ways of learning about it become less deterministic. So the big complaint about things like deep learning now is or it's not really a complaint, it's certainly something that's recognized, is some of these really extreme deep learning models come up with answers that seem to work and to be right, but no one really understands how they got there. And that's kind of part of the rub is, are you going to be willing to accept what comes out of this machine and use it, because it's very hard to go back and pick it apart and figure out how it arrived at its answer. So power. So compute is the other ingredient that's needed, obviously, for doing machine learning, AI and ML overall. I'm sure some of you are pretty aware of this. As we said, it uses tons and tons of data, but ultimately it gets, for the most part, most machine learning is taking data and using it as giant matrices. And for those of you who are not sure what matrices are, you can just think of a spreadsheet. It's almost like, you could imagine a survey, a giant spreadsheet of survey data where the rows are the respondents and the columns are maybe the questions that were answered, right? And this is how a lot of machine learning organizes its data. And some of those matrices are millions and millions of rows. I don't know if you recall, there was a couple of years, more than a couple of years ago now, they had the Netflix challenge about creating a better sort of recommendation engine. And that dealt with some really, really gigantic sparse matrices. Sparse meaning they weren't always filled in. So you had movies and then people, basically, and how people rated those movies, and then there were characteristics about those movies, and then you were trying to figure out a way to model all of that so that you could predict what other people might like. But anyway, the long and short of it is there's a lot of horsepower that goes into doing AI and ML. You need lots and lots of data to train these things, and you need to be able to do a lot of linear algebra very fast. And that's where the GPUs piece come in. So GPUs, I'm sure most of you know, a lot of people are using them to mine Bitcoin. We'll get into them one in a second, but in short, GPUs are a lot better at doing these kinds of tasks. Multiplying a matrix against another matrix is something you can do in parallel very, very well. And so a little bit of terminology here. So what's a tensor? A tensor, there's just a little bit of math here. I won't go into the exact mathematical description of it, but over here on the left, you don't even see what is a scalar value. So you could imagine just a single number here would be a tensor of rank 0, just one single number. And then just a basic list is a vector considered one-dimensional, again, matrix, two-dimensional. And then in some of the deep learning models, when you hear the word tensor, what you can imagine is these sort of multi-dimensional arrays, or just giant buckets and multi-dimensional buckets of holding information. And that's how a lot of these things get manipulated. So what is the difference between a GPU and a CPU? A GPU is very good at doing a lot of parallel operations. You got to remember what these things were created for was, they're graphics cards. So they were kind of born out of the need for being able to do a lot of really cool 3D gaming, which when you're doing three-dimensional rotations and trying to make something look a certain way, that is actually matrix math as well. That's how the computer calculates when I take this object and spin it around, how it looks. That's all linear algebra, and that's what GPUs were originally put together to do, is to make that go a lot faster. So they're really good at that, but they're not really good at doing like long-running sequential operations. So sequential meaning like I'm just going to run this program straight on through. That's where traditional CPUs really shine. They're much more optimized for doing that kind of stuff. GPUs are certainly not. They're just for, hey, I got a million of these little calculations to do all at once. Go do it. That's where they shine. What else? They tend to have less memory on them as well. Traditional CPUs have larger cache sizes. GPUs generally a lot smaller. But you can kind of see here, they kind of allude to it. The vast majority of the GPU's die surface on the silicon is mostly made up of small mini processors, whereas a traditional CPU, you've got a large cache structure, a controlling piece, and et cetera, et cetera. So this is sort of a interesting little piece, I guess. So that is the stock price of NVIDIA, which is probably, as you know, one of the largest GPU manufacturers out there. They were kind of the beginning of the market. Gamers, that was the card of choice for a long time. You kind of see here, I don't know what happened in 2016, but somebody must have figured out that AI and ML were going to be a really big thing. There could be some other events in there, but the crux of it is that they're doing quite well. And if you had invested some money, this is not a stock tip, by the way. I have no idea where this is going to crash. Could crash tomorrow. But yeah, and NVIDIA has a framework out there called CUDA, which is a sort of framework that they have for you can take even other kinds of, you can basically do regular type programming and try and map it onto these GPUs. And in some scenarios, depending on what you're doing, if you have a lot of parallel things that can be done, it can speed things up quite a bit. I think most of those things are done in C, C++, and Fortran. Somebody may have a Java hook into it somewhere along the line, but let's see. All right, so next you get this, the TPU from Google, of course, the Tensor Processing Unit. There's not a lot of information about this out there, surprisingly detailed information as far as what the actual hardware is made out of. People say it's really just a bunch of GPUs kind of smashed together in some kind of really cool way to make it optimized and be super fast. Their tensor processing unit was part of the AlphaGo challenge when they beat that guy Lee Sedol, the Grand Go champion. That happened very recently. They did say that. They did tell people that they did use their TPUs as part of that. They kind of took the graphics piece out of GPUs. That's what I've heard. NVIDIA, their GPUs they're still making, they'll still do the graphics, like the texture mapping and rasterization pieces that they were originally designed to do, which is, high-end graphics cards. Google kind of yanked that out. And it was interesting here is they do apparently like each tiny little calculator or CPU on the board, it only does like 8-bit precision calculations. So it's like super, super low precision, but extremely high, input output and number of floating point operations per second. And I got this literally off of the Google Cloud page today. You can actually spin up a TensorFlow instance, and I don't know what it costs, but you could actually engage one of these Pod Alpha TPUs, which does 11.5 petaflops. And all of these hardware accelerators, you could train a really complex piece of neural network or any other kind of involved API or AI piece that you're trying to build on regular hardware. The problem is it's just going to take a million times longer. And if you had enough hardware, you could make it go really fast. But it's just so cost prohibitive. That's why all of this stuff does run on GPUs. That the training time is just so much faster because of the fact that all of these big matrix operations can be distributed in parallel across all these thousands of cores. Where'd my cursor go? All right. So more on the why piece, the actual why piece. So, traditional this is the world we inhabit, which is more or less, for the most part, we're writing algorithms all day long. You could sort of imagine that a single program is really just one big algorithm or a collection of algorithms. They're quite exacting and rigorous. We don't leave a lot as software developers up to chance, hopefully. And at the end of the day, any function, any algorithm, any program you create is really just mapping inputs to outputs. That's really what we're doing. We are, saying for this input, we need to go and write some code here that's going to generate this output. That's effectively what we're doing. And during that time, as you're sort of going about your business and writing code, there's complexity that creeps up into software over time. The space is effectively the amount of memory you need to run the program. If you create a program that it requires so much space, it's kind of useless. Same thing with time, how long it's going to take to run. And over time, as I said, these things get really complicated. What we talk about when we talk about this is again from my deck, looking to think about how you're going to start to write software, or how you're going to begin to shift your thinking when it comes to ML, is to start thinking a little bit more statistically. And the quote I have here is actually a piece from a book. There's a really good book that I read recently that is I've got it at the end, but the author Pedro Domingos basically says that doing AI ML work is sort of the inverse of programming. Instead of putting together algorithms that you're mapping inputs to outputs, you already have the inputs and outputs, and you're producing the algorithm. That's what the machine learning system is actually doing. It's you say, I've got all of these different kinds of inputs, got all these different kinds of outputs. I have no idea what created that in the middle. Go find it. That's effectively what they're doing. Sorry. So, what does this mean? Way back when people say, and this is where I get back to saying data is the new oil, in the original Industrial Revolution, people said oil was the fuel for that. And the Industrial Revolution automated a lot of manual work for people. The Information Revolution, which was, sort of the, late 90s to early 2000s, automated a lot of our mental work. And AI is effectively automating automation. That's sort of the next frontier in all of this. And as companies kind of grow, there's these phases they go through, and I really simplified them here. And when you start a business, and I don't know if you're painting houses or whatever you're doing, a lot of what you might be doing by way of your billing and everything else is done completely manually. The next phase is automation, right? I'm going to go get some computers. I'm going to go get, as the company gets even bigger, I'm going to get programmers, and I'm going to get a staff, and I'm going to start automating this stuff. And then the third phase is finally, I can't automate things fast enough. And that's where AI is starting to creep into a lot of big companies today. I can't keep up because, I can't write the stuff fast enough. I don't have enough people. I don't have enough time and money to keep this thing going. And that's where you see companies that are way ahead of this are your Amazons, your Walmarts. They're very large. And you could imagine that, as an example, a Walmart or an Amazon, they have millions of customers, millions of products. Those products are changing every day. Could you imagine writing rules or software that could keep up with how many products and how many people are involved, how you distribute the recommendations? That's where AI and ML is starting to creep into this. The kind of work that we're doing is that recognition that these big companies, they're already there, right? They've realized that they can't keep up. They had to do it out of necessity. But eventually, over time, what you're going to see is AI products and things become more and more sort of commodity. Companies who are willing to adopt a lot of these strategies are ones that can kind of keep ahead of the other ones. So this is again from my other deck. Just summarizing data is a strategic asset. It's the new oil. It's what everybody's trying to keep. This is why people give you loyalty programs and all these other things. They don't really care about giving you discounts. They want your data. They want to track you. Because it sounds a little bit Orwellian, but really it's also about improving your experience as a customer, improving the products you get, improving the service you get, et cetera, et cetera. And then as far as the overall business advantage, there's a little quote here about a bank without a database can't compete with a bank that has data. Sounds very simplistic, right? But it gets back to that sort of like first and second phases of the growth of a business. There's just no way that somebody doing something completely manually or with very minimal automation is going to be able to keep up. You can't imagine a bank, how it could grow if they were doing everything on paper today. It's not even possible that they would be in business. And without automation, this is another quote I've heard too in a number of books, is that software development will eventually be seen as the bottleneck. Getting back to that fact that as companies compete with each other and everybody adopts more automation and more machine learning, there's going to be more pressure on engineering to adopt some of these strategies to get things done. So finally, some other quotes here. So this is very recent. This is just the overall, what Gartner sees as being the value of AI. And AI here is just being used as a blanket term. Again, it's that whole spectrum of stuff all the way down from basic automation all the way through to deep learning and things like that. But expected within 2022 to, the value, and there's various ways you could sort of quantify that. Starting right now, they estimated for this year at 1.2 trillion, and then by 2022, nearly $4 trillion. So this is, I think, I can't remember where I collected this one from, but this is just the overall sort of growth of the market. Between those 4 years, it grew at 34%. 34% compound annual growth rate on the patents being granted. So this is another thing too. A lot of the analyst companies that are out there that are saying that most of what they're expecting the growth in AI and ML to be is going to be in these niche companies that do one specific thing with AI, ML very, very well, as opposed to sort of going out there and trying to be everything to everyone. And then just overall spending by 2021. So that's spending, right? $56 billion from $12 billion, or I don't know what it is in 2018, but that's a lot of money. and then the number of actual pilots. So this is interesting. In 2018 compared to 2017, and then double again by 2020. So this is actual software projects, right? Implementations of things using AI and ML. Expect however many there are today. They didn't give that data, expecting it to double in 2 years. So that could be huge. And then finally, this is always the interesting piece. This is again put out by Gartner. It's the hype cycle, I think it's called. But I always find this interesting. Deep learning, machine learning, at least I think this is from, it's from last year. It's a year old, but they're still saying this thing is at the peak of where people's expectations are. It's super hyper inflated as far as what it's actually going to be able to do. And it'll take 2 to 5 years for that to eventually come out. But the things that are kind of leveling out here is speech recognition, which I think I might agree with that. I don't know, when I talk to Alexa and things like that in Siri, I don't know how much better it would get. It is sort of leveling out and getting to a place where I think it's gonna sort of be done, not done, but there's not going to be any riveting sort of things that come out of it. And then the other things here too are AR and VR. I know that's been something that people have been closely watching. They're sort of not there right now. This is the trough of disillusionment, which means basically it's not living up to what we thought it would.
Hey, Carl.
Yeah.
What is the definition of ensemble learning?
I don't know.
Okay.
I have no idea, but do you know? I don't know what it is. And then finally, this is the really cool book. I think he has a lot of really cool ideas, this guy. He has some crazy ass ideas in there too. He thinks that there's going to be one master algorithm that they'll be able to sort of learn anything with. Whether or not that actually happens, I don't know. But it's a very interesting read nonetheless. He goes through a lot of the sort of setup stuff that I talked to you about, and how companies that are able to do more AI and ML are the ones that are going to be able to compete versus the people who are just saying, hey, I'm just going to keep writing more and more software with more and more people spending more and more money.
By the way, Carl, ensemble learning, which is something it's like image learning and classification learning.
Oh, so pattern recognition, classification of images. I don't know why. That's weird because.
Oh, so I looked it up too.
I mean, technically, deep learning does that too.
I believe it was more instead of it was a process of machine learning. So it was like training a bunch of bots differently and then like leave stuff out. Stuff like that's what it was described as.
There's something called swarm learning, which is based on, there's this place called the Santa Fe Institute, which does a lot of research on game theory and how ants organize. And there's an aspect I know of that in machine learning where they do a similar thing. They sort of conquer it through many sort of agents, as they're called. But anyway, that's about it. If I do another one of these, I think it'll be specifically on deep learning. Because I was trying to come up with trying to hit a few of the components inside of AI and ML. And at this point, there's so many of them, it would take 3 hours to go through them. And I didn't think you guys would find that interesting. So any questions? Yeah.
Have you seen any AI ML project within auto market as well?
In Slalom?
Yeah.
Yeah, I mean, we are slowly starting to dip our toes into it. Specifically, I know they did one here for, I think it was Univar. There's not a lot.
I was just looking at Paul's on this actually. There was a PG&E project in San Francisco recently where they built a chatbot.
So that's what I was going to say is, what do you consider an AI ML project, right? Because it's a pretty broad thing. Is you see somebody writes a chatbot, that's considered part of it. But that's a far cry from saying I'm going to train 150 layer deep learning neural network to recognize somebody's face walking in the door.
They did have a machine learning.
They did.
Yeah.
Okay, that's
I
cool.
don't know, it's not about it.
Yeah, there's a lot. Slalom has certainly done a lot more data science, and that's one thing we didn't talk about. But precursor to a lot of this stuff is the exploratory aspect of machine learning. Because everybody's so hyped up on deep learning now, which is more like, hey, I don't know anything about data. I tried to figure it out in very, very rough terms, Mr. Computer. But most of the basic analysis that people do and try to put in place for the simplistic recommendation engines and things like that, those are more, hey, I've got a team of data scientists. They're going to go pull in all this different data from all over the organization. They're going to build some models that give the company some sort of insight or edge into what they want to do for their customers. And then they take that and they go sit down with the groups of engineers and say, okay, make this into software. So we've done a lot of that for sure.
So earlier you mentioned with the GPUs and the training process of it that we're using those just being time saved, right? Program that's output by the training, is that, and this is dependent question, but are they also generally running on the same hardware they were trained on, or
no? Actually, once you're done training, they run ultra fast.
Yeah.
So it's the training part that takes forever and a day.
Right.
You can once what pops out is some sort of model with some sort of for lack of a better term, function or API that you're going to call. You're going to send the same inputs into it that you use to train, and then try and get some kind of output, whether that's a match against a photo or a yes, no, or these are the products you need to put in front of the customer. That once you've got that thing trained, you could run it on a phone.
You're not dealing with a giant massive data
anymore. At that point, so going back to what I said earlier, our job is writing algorithms. This is here's the inputs, here's the outputs, give me the algorithm, and then once you have it, it's just a function call. So it's the training part. And some of these really big ones, I mean, they're even when they run them on decent sized group of GPU machines in AWS, some of these big 150 layer neural networks can train for a week.
So what about retraining?
So, I mean, that's certainly, as you talk about, this is something that the Slalom sort of XM IM&A group is trying to sort out with how to go to market with AI and ML, which is these bigger questions of not just how do you get what you built into production, right? There's a million ways to do that. There's actually a company out there that started that 3 or 4 years ago called Algorithmia. I saw them at reInvent, but they basically created this idea that you can build your models in all the common frameworks like MXNet, ImageNet, they're built on top of AWS, you upload it, and then they have some process where they turn your model into an API. And then they actually created the idea of like a store, like an algorithm store, like where you could actually charge people then, depending on what you built, to be able to use your API. I don't know how much that part of the business is working, but anyway, that part of like, I've built the model, now what? How do I put it into the software? That's the operation. I'll call that the operational side of AI ML is a huge part. That's what Slalom is trying to talk to customers about, because we have so many other things we're really good at doing by way of DevOps and just general software engineering and process. But it's a dark art to know how soon you need to retrain something. I think most people will generally tell you that you need to know what you're measuring. You have to have some kind of KPI that you're measuring in your business before you even start to know, okay, this, sales are falling off over here. It's time to start retraining. Netflix has a lot of, I think they have a lot of blog information about that out there. I know that one of the things they do is they have sort of the blue-green idea where they have such a huge user base. They'll design some new model that they think can tweak something, because their whole thing is about, one of the things they do is, which photo do I put in front of the customer to get them to want to watch it? And they have all kinds of algorithms about who you are, because the photo that I see is not the same photo, not necessarily the same photo you will see. And that's based on my viewing. And they have some models that say, Carl would really like a picture of a cat, right? If there's a cat in the movie, put that up there and he's going to watch it. That's what they're doing. And so what they'll do is they'll try new models, deploy them to a portion of their user base, look and see, are they getting the click-through that they thought they were, and then, maybe then broaden it. But it is a bit of an art. I don't know that anybody has an exact science for doing it. Anything else?
Yeah, I'll just make a plug for Nahara's community. Nahara's running the Primal community, which is AI. Machine learning, all of this stuff. I rolled my data science burden on science competency and things. So join the chat room, and I think our first physical meeting is next week.
Yep, perfect segue. Good idea.
As the AI ML industry mature, I'm sure that they've come up with a better algorithm to use on certain cases in certain industry. But have you seen any trend on like ethics portion of the AI ML?
On what?
Ethics.
Ethics?
Yeah, like
So I went to a conference last year. I think I talked to some of the essays just quickly about. There was one person, I can't remember where he was from, who did he didn't have answers to this stuff, but he was, asking all of these, important questions. Let me see if I can just quickly pull it. I don't have it in here. He was, he had a whole list of questions that he put in front of the audience about the ethics of AI. Like, God, I wish hold on 1 second. I'm going to find it for you guys. 2 seconds here. I bet you I still have the photo of the screenshot.
There's also this thing called the algorithm.
Yes, that's new. That was actually, I think, spun up after this conference. I did hear about that. I don't know anything about it. Where is this dude? I don't have it. But anyway, it's to answer your question, as far as I know, it's definitely something that not a lot of people are thinking about. I think in Europe they're a little bit more progressive in their ideas about putting it front and center. Like, there was like a couple of questions were like, should I, call it robot, whatever, can a robot call the police? Can a robot inform the police of illegal activity? Is it ever okay for a robot to pretend to be a human? They had all of these really, really good questions. I don't have it, but no good answers. It's definitely something that people are thinking about, and it'll certainly come front and center more and more. Anything else?
So I'm not sure if we're at a point where a lot of companies investing a lot in AI have really focused even on that investment. Is there any data to show that there's actually profits to be made?
Return. Well, I mean, I think that slide here from Gartner, again, I don't know how who knows how they are getting to these numbers, but this is their sort of business value calculation of what, of the current amount, what AI is bringing to the table today. 1.2 trillion dollars in 2018. I have no idea how they get to that number. It's probably some all up, like, how much money did you as a company invest in AI and machine learning this year, and how much did you decrease operations costs? It's probably pretty broad brush. I don't know. I really don't know.
And I think it's hard to calculate, especially things like the networks example you brought up.
Yep.
You can't really see if the change in picture actually made you click on that object, right? So.
Well, you can. I mean, they have the data. They're always, Google. Part of the reason, Google loves image search because they get free data out of it. You go and search for an image, and they know what you typed in, and they ultimately know what you clicked on. Well, you just helped them out, right? Not that you shouldn't help them out, but I mean, they've refined that image. They know all the data points and tags you were looking for, and they know which one you clicked on. So that gets fed back into whatever models they have, and the next search in theory should be better. And that gets back to companies not wanting to go and tag and clean their data after the fact. A simple example is you go to a website today and you type in some question into the help, what's the next thing that happens? Was this useful, right? That's feedback into the model to say, yes, or, no, right? And eventually, depending on how they do their work, right, they'll either collect that and automate it or refine the model or something. But
Well, I think too, like, it's important to remember, they don't care if it got you specifically to open that up, right? They're looking at what's the probability when we display this,
right.
how many.
Oh, are you asking about like one single user, Carl? No, they don't care about Carl. They just want $11 a month. That's all they want.
Yeah, like it's all probability based, right? There's no way to know if they've never presented you with it before. Or
Right.
Like they can't understand
No.
exactly what you're thinking. But if there's like, oh, when we show this image, 60% of people with this profile end up opening.
Yes, exactly.
That's the kind of information
That's the basis of a recommendation engine, and getting back to the giant data, giant matrices, they're sparsely populated, right? So, there's holes all over the data, and they have ways of, if they put out these new image changes and 20% of the population clicked on them, they have a way to take that, sparsely populated matrix and crush it down and then say, then they can kind of map it into a lower dimensional space and say, oh, this person who did that looks a lot like that person, right? I'm going to also do the same thing for them. It's a never-ending loop of trying to refine things. So. Any other questions? Cool. Well, thank you guys. Appreciate it.